And protocol, we don't speak or walk in front of the camera when it's on, right? So just kind of avoid walking in front of the camera. Talking about significant figures, really what we're talking about is uncertainty. Let's say we have uncertainty in time when an angle of the rotating beam was observed, plus or minus a half second. Because we're timing this by a pendulum, and the pendulum, let's say, we make a mark every second. We mark a different mark right after the thing is pointing at us. Okay, and we all know what that means. So let's just say that our uncertainty is plus or minus half a second. It's a reasonable estimate. We could get much more rigorous with that. And the uncertainty in our position is 1/10 of a radian, about 6 degrees. Okay. So let's say two of our data points. Position at 7 seconds is 18.84 radians. That's a pretty good approximation, I think, of 6 pi. Okay. And at 10 seconds is 25.06 radians. And I think the difference of these is 2 pi, approximately 6.28. Okay, we want the average rate of change of theta with respect to t. Here it is. Change in theta divided by change in t. And really, I should probably flatten this out. It's 10 seconds minus 7 seconds. Okay. So that equals 6.28 over 3. This is radians. This is seconds. Okay, well, that equals, I'll just approximate it through significant figures, that equals 2.09, and it rounds off to 2.09 radians per second. That makes sense? I'm not asking if it's accurate, who knows, but does it make sense? Okay, it's a rate of change. Change in this divided by change in that. That's what a rate of change is. And as we talked about last time, if you want an instantaneous rate of change, that's a derivative of your position function. You want to keep pondering that till to refer to. All right, now the point here is with significant figures and so forth. For all those figures, how much significant figures are there in 2.09? 3. Okay. You ignore leading zeros and count everything else, right? All 3 of those figures mean anything at all? No, because as far as you know, this could be 6.5 seconds. And this could be 10.5 seconds. Okay. You have this plus or minus 1/2 second, right? Now, in the actual situation, probably would be 6.5 seconds. It could be 6.1 seconds and 10.9 seconds. Okay, there's like could be a 1 second swing in this, so this denominator could be close to 4. That gives you something complete. It gives you like 1.5 radians per second. Okay. So that 0.09 doesn't mean a darn thing. Now, the way we say that is there are really only 2 significant figures in this number and 2 in this number. Okay. The change you have here, well, it's probably round that off to 19. So if we do t and theta, I'll use the numbers here. This is going to give us just as good a result as this does. And if we do this, then we see that the average rate of change is approximately equal to and you get 2. Okay. You don't worry about all the change you've got out here if you can't observe it accurately. You haven't observed anything after the 3 significant figures. You pretty much got 1 significant figure. Okay. Well, that's the idea. You can read about it more in your text, and you probably know a lot about it anyway. Okay. But if you don't, you get it. So the first thing you're going to see is some questions about significant figures. I'm not going to go through all the rules. You can read them. They're not difficult. And really, I don't even necessarily like all the rules because, well, we'll discuss this for just a second. Don't say anything now because the camera's still on, but we're going to discuss this question. Does anybody know what a differential is? Oh, phooey. Okay, what we said was, if we have this, what's Vy, what's Vx? Well, Vy is the magnitude of V cosine theta. Magnitude of V is how long this side of this triangle is, and theta is the angle, and the Vy side is adjacent to the angle. And the Vx side is equal to this, or if you want to just look at this triangle, the Vx side is the magnitude of V times the sine of theta. Okay? As I'm saying, it's very simple. We're only dealing with right angle trig in this course, for the most part. There's one place in second semester where people like to use the law of cosines. That's not that hard either if you know the right angle trig. It's just a slight modification. Okay, well, there's a little more. So let's say you have a vector here. And you know Vx and you know Vy. Then what's the magnitude of V? And what's theta equal to? Okay, again, I'm saying a lot of circular answers. By circular, I mean this. I ask you for the magnitude of V, I ask you for theta. So that implicitly means we don't know what V or theta is. Okay? So you can't say that the magnitude of V is, or that magnitude of V is Vx divided by cosine theta. That is a correct relationship, but you're using theta, which you don't know, to calculate V, which in turn you don't know if you're trying to use theta to do it, right? Okay, so you want to keep that in mind. Now, another answer I saw was correct expression for V, okay, magnitude of V. And then we do the arc cosine of Vx over cosine theta, okay? I'll write it out in a minute. And that was really good. And the only problem with that is you use the calculated value to indicate the result. And that's what I was saying when I said that can lead to cascading disaster, because if you didn't calculate this right, you're not going to get this right. I can write expressions for this and this that don't depend on whether the other one's right. And it becomes easier to check my work for consistency. And especially if you're going to be an engineer, you want to ponder that idea. Check for consistency, because what you build has to work. If you're a physicist, you just build it, it blows up, you build another one. Nobody gets hurt, hopefully. Okay. Now you don't want to do that. You don't want to waste your energy. But in engineering, especially when what you're doing directly affects people's safety or their utilities or whatever, you're going to have plenty of checks. You don't want to crash your Mars probe into Mars because somebody put down a number that was in pounds when it should have been in kilograms. That was a multi-billion-dollar disaster back in the 90s. Okay, before your parents were born. Okay, not that one. Okay, so what's the magnitude of V? Magnitude of V is how long this is. You heard of the Pythagorean theorem? Well, I know you have. Just square this and add it. It's Pythagorean theorem. And then you take the square root of Vx squared plus Vy squared. Okay? Now again, these relationships, there are only about 4 of them that you have to know. And then how to use them. Okay? And using them is kind of easy. And the homework is going to do a really good job on that. Okay? Theta. Well, let's write off something here. Definition of the tangent of theta is Vy over Vx. Okay? I'll put the abbreviation DEF down here. Not that it can't hear, that that's the definition of the tangent. Okay? So theta is just net tangent's a function. We do the inverse function. Okay. Then I'm going to say plus 180 degrees if Vx is negative. That'll put it in the right quadrant. The inverse tangent is in the fourth or first quadrant. You got a negative here, you got an angle in the fourth quadrant. If you have a positive Vy over Vx, it's in the first quadrant. But the tangent is also positive in the third quadrant and negative in the second quadrant, and you don't know which one it is unless you have the picture. Or unless you do what I saw a couple of people do. Another thing somebody said was said that Vy is the magnitude of V times the sine of theta plus pi over 2. It's absolutely correct. I'm not going to talk about that until later. Okay, it's important. It's good. It shows good knowledge, good depth of knowledge here. And that's correct. And really, I prefer to do everything in circular angles anyway. Then you don't have to worry about quadrants. Just have a calculation scheme get you the right answer in a way that really makes sense. Okay. The book does it differently. The book was written by people who know almost as much as I do on their better days. And I'll respect you for that. Okay. But it's kind of a disrespectful respect. I got to maintain my independence. Okay. I'm very respectful. It's a great book. I learned out of the second edition of this text. It's up to the 15th edition. They do about one edition every decade. That makes me over 150 years old. That's about right. Okay. Got to know this. Now I got to look at what else, because I really anticipated being able to move through this a lot quicker. I think you're going to have to dig a little more because I'm not going to change the order of the assignments because you have no idea how terrible that will make the end of the semester when everything has to be done at once. Okay, you probably do have an idea because you probably experienced that in some of your courses. How many have had linear algebra? Okay. There's dimensions. Yeah, we can get a little out of that, I think. We'll see. Okay. Yeah, no, it doesn't have to be next week. Oh yeah, dot product. Okay. Now let's say you've got a vector here. And we can indicate that vector in a variety of ways. I think mastering maybe uses less than and greater than signs for the left and right to indicate that it's a vector. It'll tell you how to enter the answers, okay? And I think actually maybe in the introduction, which I think not everybody as of this morning was signed into the master in physics stuff. Okay, you need to get that done. Probably going to extend that assignment and the other one to Tuesday, but that's not going to change the fact that chapter one, part one is also Tuesday. It's a lot of stuff. You're used to a lot of stuff. That's okay. But make sure you leave yourself plenty of time. Try to get it done as much as possible before the weekend so you can enjoy the weekend and then panic on Tuesday. Okay? And try to do better than that. Try to get it so you don't have to panic on Tuesday. Okay, so here's a vector V and here's a vector W. Which, unsurprisingly, will indicate as WX, W1. Okay. Okay, there are plenty of connections to this for linear algebra. This is defined in linear algebra. You get to the point where you use formulas to do things without thinking about what they mean. I think most people have to. Okay, if you really master it, you understand how everything, orthonormal bases, Hermitian matrices, unitary matrices, similarity transformations, everything. It's a lot simpler if you understand what follows from this. Okay. Now I asked for the definition. I know some of you haven't had linear algebra, so I'm not going to talk that much about it. I'm just trying to make the point of try to understand things as deeply as possible, given the fact that you don't have time to do that. Balance that as best you can. Okay. Dot product. Actually, I'm writing down the second thing you told me. The definition is Vx Wx plus Vy Wy. Very simple. I think I said it right. I'm going to write it correctly just to make sure. Okay, that's it, right? I didn't screw it up. I didn't do two V's here, two W's here, or anything. Okay. And it's equal to this. So if you know these components, you can calculate the dot product and you can calculate the two magnitudes. So then you know what the cosine is, right? And then do the inverse cosine and find the angle. It's very, very simple. Now the applications and how you get from there to orthonormal bases and Gram-Schmidt and all that stuff comes down to projections and stuff. And projections are important. Okay. I don't think the homework does a whole lot with projections, but if we find out differently, because I don't remember everything I looked at this morning. Okay, don't remember if I noticed that detail. Actually, I can find out. I've got a copy of the text I never looked at. So I don't do their trigonometry, circular angles. At least I can do is not look at it, right? That's the only reason I look at it. Make sure I've got a notation that's consistent with theirs. Now projections do come up, and so do unit vectors and stuff like that. And right there's a scalar product, that's your dot product. But see, I don't know where part one and part two split. they split before you get the vector product. The last thing before vector product, cross product, which a lot of you know about and talk about next week because it's not in the homework for Tuesday. Okay. So the last thing is scalar product, the dot product. I don't see anything about projections at this point. I might have missed it because I just glanced at the paper. But if projections are important, it's not that difficult once you understand the scalar product a little bit. Use some problems. And the projection is just, you want to project V and W, you just do this. Right there, the projection. Okay. And all it is V cosine theta multiplied by a unit vector in the direction of W. Get a unit vector by dividing W by its magnitude. There you have it. And you don't have to understand what I just said, but in case you do, that's just to jog your memory a little bit, okay? Don't want to spend any more time on it than that. Okay, so we had a very brief discussion. First of all, I wrote down the fact that we're going to look at dimensions. And then we're going to look at units. Okay, first we'll look at dimensions. Fundamental dimensions are length, mass, and time. Fundamental quantities in physics. There are a couple of others, current, amperes, and a couple of others that are fundamental, but they're not going to be relevant this semester. We'll get those when we need. So if I don't know if this is going to roll or not, if I roll a piece of chalk, well, okay, well, it spun, which took up some of the energy of my flick, and I don't have enough energy to do it again. So, but it went from here to here, right? Now, if I want its average velocity, let's say between here and here, the question I posed was what I need to know. Well, what I need to know to get the average velocity is how much position change. In other words, its displacement, okay? And what would the units of displacement be? Well, immediately got an answer. That'd be units of length, right? Your displacement is a length, it's also a direction. But you subtract two quantities. Position here is a length, position here is a length from wherever you started, and you subtract those two, you get the displacement, right? So it's got units of length. And then you divide that by units of time, right? So we can say I'm writing really badly today. I don't know why. I mean, it's pretty bad every day. It's pretty bad. But I said the dimension is therefore length over time. Everybody understand that? So what would the units be? What convenient units would we use here in the lab? High units. Okay, now when I asked what would the units be, somebody said, yeah, miles and years. I rolled a car across the tabletop about like that. Okay. In SI units, it would be meters over seconds, which would abbreviate and over S meter per second. Okay. Okay. Let's see. Convenient units for some measurements might be centimeters and milliseconds. It's easier to think 140 milliseconds than it is 0.0140 seconds. Something, okay, 140 is easier to visualize than 0.014. Okay, maybe. So there can be an advantage using different units. The units might be centimeters over milliseconds. That's not meter seconds. If it was meter seconds, you'd have a dot to indicate it's meters times seconds. Okay, you could write out milliseconds or milliseconds. Okay. Be able to work in SI as much as possible because your derived units, like the unit of force, which is the Newton, is defined in terms of the SI units for length, time, and mass. Okay, kilograms, meters, seconds. But conversions are easy, especially in metric. I'll say SI or whatever. If you want to express it in miles per year, all you got to do is know how many centimeters there are in a mile. Okay. And how many seconds there are in a year. Yeah, 3.6 million seconds. Okay. Meters in a mile is around 1,600, so it'd be about 160,000 seconds. You can make the conversion. It's not difficult. Okay. Takes a little bit of writing, a little bit of care, make sure it makes sense. And you learn about conversion. I'm not going to teach that, but if problems arise with it, in the press. Okay. So that's it. Well, I talked about some of the derived units. One of the important ones is the unit of force. Now, the units can be in any system that's convenient to what it is you're trying to observe. Any set of units that make more sense, where the numbers make more sense. Okay. What's the diameter of an atom? Well, around 0.0000000001 meter. Now it's 1 angstrom. Okay. Yeah, they go up to 3 or 4 angstroms, I think. Nothing too much less than an angstrom. Bare hydrogen atoms about an angstrom. The electron has a mean distance from the proton of 0.529 angstroms. 5.29 times 10 to the negative 11th meters. Okay. You want to work in numbers that make sense. So you use a system of units, but the dimensions are what the dimensions are. They don't change with units. Once you know the dimensions, you put any set of units you want on those dimensions, right? Well, get back to the quantity. Net force is mass times acceleration. Net force is vector. Net force, for future reference, is the sum of all the forces that act on the mass. Okay. Not whatever force you happen to exert. There's also force gravity probably exerts if you're in a place where you can survive. We'll talk more about that, but it's kind of one of the foreshadow of something. Okay, and as your acceleration, which is just the derivative of your velocity, the rate at which your velocity changes, the instantaneous rate of change of your velocity. Okay, Well, that's great. What would the units of force be? First of all, what are the units of acceleration? Well, velocity is the rate of change of position. Acceleration is the rate of change of velocity. What are the units of velocity? Well, we just worked it out. Your change in position is in length. Divided by time. Acceleration is change in velocity. That's length divided by time over time. Which is length over time squared. In SI units, it would be meters per second squared. If we're dealing with that cart, we would probably want to do it, and we're going to do it. We probably want to do it in centimeters and seconds. Okay. And you'd have centimeters over second squared, right? In SI units, it'd be meters over second squared. And that's also meaningful for that car. Okay. Depends on how you want to think about it, what's the most convenient way for you to understand what you're seeing and what you're measuring. Okay, well, that's acceleration. Now, what about mass times acceleration? Somebody want to take a stab at that? Okay, so any units, well, okay, there's your acceleration force will be mass times length over time squared. SI kilogram meters per second squared. Okay. Okay, if convenient. Probably can't read that second word. Milligrams times millimeters over milliseconds. With all those millis, well, you've got a milli squared in the numerator, you got a milli squared in the denominator. So this would be the same as gram meters per second squared. Okay, we got a question. I might have made a mistake here considering. Okay, so what I said is you got a couple of millis here and you got a squared milli here. So you got your millis cancel out, don't they? And you end up with gram meters per second squared, which isn't quite SI. Well, if you want to go to kilograms, a gram is a thousandth of a kilogram. So this comes out millikilogram meters per second squared. You get a mill back there. Kilograms, a thousandth of a kilogram. You probably don't understand that when I just kind of ravingly say it. But you want to be able to think, develop the skill to think about units in a way that's going to help you make sense of what you see in lab and what you also see in the problem sets. Fair enough? So, big chunk, when I took physics, sort of not top of the top notch, but a pretty top notch school of engineering and science. Every freshman, if they didn't have some kind of advanced placement, people from the prep schools in the East sometimes came in already knowing enough calculus. We had to take an accelerated calculus. But we took calculus-based physics, calculus-based chemistry, and a calculus-based calculus course. Calculus course. rigorous engineering calculus, much more rigorous than most of the courses that are taught these days. We had to prove things, okay? I came from pretty good school. It wasn't one of those top-notch Eastern prep schools, okay? And I felt for the first semester like my whole brain was being rearranged. And, learning calculus and calculus-based physics together. It's a great experience. I learned stuff. And by the end of the following year, I'd had it sorted out, but it took that long. Okay, so there's stuff you got to sort out. Maybe you know a lot of it, maybe not. Nothing I said here, nothing we did here is all that complicated. There's a lot of it. And if you haven't done a lot of it, and I wouldn't have survived if I hadn't had a very rigorous trip. All the stuff with vectors, was second nature to me. I said, why do we have to draw these pictures? I know what this is. Okay. There's a lot of stuff I didn't know, like I hadn't had pre-calculus. That was interesting. But my whole point is no matter what your background, there are going to be things that you're going to wish you knew better, but just hit it as hard as you can. Put it together. It will sort out if you stay at it. Okay. If you've been through the courses you've apparently been through, you're smart enough to do it. And hopefully you're in a life situation where you have the time to do it. Okay. People get through. Some better than others. But pretty much people go on to tech and do okay. Good track record for people who have these questions. Okay, well, let's make everything we do to not only pass the course, but do really well. Because the better you do, the better you're going to understand the engineering that you're going to learn later. If you're an engineer, and if you're in some other field, if you want to be a mathematician, I don't know of a rigorous mathematics degree that doesn't require calculus-based physics. Okay. If you're going to major in something else, just learning to think the way you're going to learn to think, to solve problems in physics, and your problem-solving ability is going to be valuable to you no matter what you do. Okay. Okay, I ran over 5 minutes. I'm sorry. Go on with your lives.